Hello. So far in this course, we've been talking a lot about regression models and endogeneity and causal effects and all that sort of thing. And we've talked about causal effects and the endogeneity problem is having to do with stuff that's in the error term that is related to whatever our treatment variable of interest is. And the way that we can handle that is by taking the terms out of the error term and including them in our model as control variables. Now, an obvious problem with this is that there's probably a lot of things in that error term that are related to our treatment variable and also to our outcome, giving us endogeneity problems. And if what we're doing is we're trying to solve this problem by controlling for stuff, at some point we're going to run out of stuff that we can control for. Right? We're not going to have all the data that we're going to need, right? If you're, doing some sort of thing about the effect of schooling on earnings, well, maybe one of the things that relates to both of those things is like your personality. But we might not have a personality measure for every person in our data that we need to deal with. So if we don't have a variable, we can't include it as a control, which means that our endogeneity problem might persist. It won't be solved. So for a lot of the rest of this course, what we're going to be doing is talking about ways in which we can still identify causal effects that we're interested in, even if we can't measure and control for everything that we need to control for. And the first way that we're going to be talking about is the use of fixed effects or within variation. And that's what we're going to be talking about in this video. This one might be a little bit longer because I'm going to try to get at all the different aspects of within variation as opposed to splitting it up into multiple videos. So it might take a minute, but we will get through it. I think it will be worth it. So, as I mentioned, we're in a situation where we have a causal effect that we're trying to get. We're trying to get the effect of X on Y, but we are worried that there's a lot of things that are on back doors. If we were to draw out our causal diagram, there'd be lots of alternate explanations for how we could get from our treatment to our outcome that are not just going on the path that we want. But we can't control for everything. There's just too much stuff on there that we can't measure. So what can we do about it? Well, one thing that we can do is we can say we can control for some stuff even though we can't measure it. And in particular, the kind of things that we're going to be able to control for are between variation. So let's talk very briefly about what between variation and within variation are. So let's imagine that we are in a situation where we don't just have some data on some people or whatever. We have data on the same people or the same companies or the same countries over and over again across multiple time periods or years or months or whatever it is. This is what's called panel data. Here's an example of what some panel data looks like. You can see, so this is some data from a crime data set. It's got different counties in it. So here's county 1, here's county 3. It covers these counties over different years, 1981, 82, 83, 84, all the way through up to 87. And then we start over again with a different county in 81. We have different crime rates and probabilities of arrest in these different counties. And these are just the first few rows from this data set. Of course, it goes on to contain many more counties. But the key here that I'm trying to get across is that this includes the same counties over and over again. So we can see the same counties multiple times. That's what panel data is. There is both a cross-sectional variation, we would say, right? There are different counties that we can compare to each other. There's a cross-section of counties. There's also a time series element where we observe the same counties over multiple periods of time. But when we have both of those at the same time, we can call that panel data. So what does it mean that we have panel data? Well, when we have panel data, we can start thinking about two different ways in which these numbers can vary. So we have the crime rate here, okay? And we might think, okay, why is one observation of the crime rate different from another observation, right? Well, if we look in this one, first in county 1 in 1981, the crime rate is 0.0399. If we look at this one over here in county 3 in year 82, the crime rate is 0.0191. Those are two very different numbers. Why are they different? Well, there could be two things we can sort of divide it into. One thing is that we're comparing different counties, right? County 1, if we look at all these numbers, appears to have a much higher crime rate than county 3. But that's not all that we are changing. We're also not just looking across counties here, we're also looking at different years. So here we were looking at 1981, here we're looking at 1982. And so it could well be that, part of the explanation for why we see these different numbers, part of it's going to be that they're different counties, and also part of it's going to be that they're different years. Maybe some years have more crime than other years, as we can already imagine that some counties might have more crime than other counties. So we have two different forms of variation, reasons why the numbers vary. One is the between variation. Between variation is the variation between the different counties, the different individuals, the different countries, whatever our sort of individual is that we are observing multiple times. The other kind we might have is called within variation. Now, within variation is not comparing one year to the other, as you might think, because the first one was comparing individuals, and now we're comparing years. No, that's not what it is. It is comparing years, but specifically within variation is comparing one year to another in the same county, right? So it's not that I'm comparing this 0.039 to this 0.190. It's I'm comparing this 0.039 to this 0.038, okay? So we can go from one county to the other, that is going between counties, that is between variation, or we can go from one year to another in the same county, and that would be within variation because it is varying within a county. So we've got two different kinds of variation. Let's look at a quick example here. So here are 4 counties from that data set that I pulled out, and I've got the different years that we have for them, and I've colored each county separately. Now, given this, you can sort of see that, first of all, there are big differences between the counties. County 1 has a cluster up here, County 7 sort of over here, County 3 is down here. So there are clear differences between the counties. But there are also differences within the counties, right? The crime rate is not the same in a given county from year to year. It does vary a little bit. We can break this into the between and within variation. Now, if we're looking at the between variation, what we're really doing is we're comparing the means of each of these counties. So I've got the crime rate over here. I've got the mean crime rate for County 23, the mean crime rate for County 1, the mean crime rate for County 7, the mean crime rate for County 3. And I got the probability of arrest down here. I got the mean probability of arrest for County 3, I got the mean probability of arrest for County 23, and so on and so forth. And so basically what I'm doing is I'm marking off each county's means, both for the X variable, the probability of arrest, and the Y variable, the crime rate. And this is giving each county its own set of axes. So we can imagine we got 0 and 0, and if we draw a scatter plot, here's a point where it's with some crime and some probability of arrest, here's another one, 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 but here's 0 and 0. But instead of using 0 and 0 in the same set of axes for for all the counties, instead we're going to let each county have its own axis, and those axes are going to be centered at the means of the county. So if a point's over here, that means that it is, from my perspective, if we look like this now, it is a higher probability of arrest and a higher crime rate than the county would typically be. It is above average for both of those. If it's down here, that means that it is an above average probability of arrest, but a below average crime rate, right? Everything is relative to those mean axes that each county has their own one. So between variation is looking at the relationships across the crosses, right? So each county has its own mean. If we just look at those crosses by themselves, we ignore the year-to-year variation, then we are just looking at the between variation here. On the other hand, if we look at the dots themselves and we move all those axes together, we are ignoring the differences between the counties, right? We're ignoring the between variation and saying, let's imagine that every county had the same axis, right? So it's not we're forcing them to have the same axis. We're saying, I know you have your own axis. I know you have your own axis. I know you have your own axis. But we're going to sort of move everybody together so that we can look at everybody from the same perspective. So relative to everybody's own means, is this particular point high or low on different axes? And what we can do is, and what we're doing when we look at just this within variation, is we are removing all the between variation, right? You can see that all the between variation was the differences between the different axes. And so when we get rid of those differences, when we slide everything together, we are getting rid of that between variation. Now, what happens when we get rid of a certain form of variation? That means we are controlling for something. So, by taking the means within each of the counties for both the X and the Y variable, and subtracting out those means, bringing the axes together, we are controlling for the between variation. We are controlling for all of the differences between the counties. Now, there still remains variation within the counties, and that's what we're looking at here. But we are controlling for all the differences between the counties. So everything that is only different between counties, everything that's constant, that is a difference between counties that is constant over time. So, for example, something like geography. County 1's over here, County 4 is over here. Those things are always the same, right? Those aren't moving from year to year. Because they're not moving from year to year, it's entirely between variation, right? For it to be within variation, you'd have to change from year to year. But this county doesn't move around from year to year. It's always in the same place. There is no within variation. So if we get rid of all the between variation, suddenly we're acting as though there's no difference in geography whatsoever. So if geography was something that was on a backdoor, we would have controlled for it by getting rid of that between variation. And this goes for anything that is entirely between variation. When we get rid of those means and slide everything together, we are controlling for everything that is constant over time within county. Okay? So everything sort of unique to that county that does not change very quickly over time, we have control for, even though we didn't measure it. We don't need a measure of geography to know that getting rid of these means controls for geography. We don't need a measure of like town pride or like history. As long as those things don't change over time within our sample window, then we're controlling for it because we are getting rid of all between variation, and those are only existing in between variation. They don't have any within variation. So if we control for between variation, we're controlling for those things. And in doing so, we will have control for everything we need to control for to get rid of all of the between variation. And so if there's no endogeneity problem with the within variation, if all of the endogeneity was between, then by controlling for the between variation, we have identified our effect. We have gotten rid of the endogeneity problem. So how do we actually do this? Well, we're going to use the process called fixed effects, and there's two main ways to do it. And by fixed effects, it means what we're referring to here is that we are looking at the stuff that is fixed within individual or county or country or whatever it is, and we are controlling for it. We are adding an effect for that fixed part and getting rid of it. Here's what the equation looks like. So typically, in a regression, we would just look at, here's y, here's our intercept beta, here's our slope beta 1, here's x, here's var epsilon, or here's epsilon. And all that if we have panel data though, if we have some fixed effect in there, if there's something that is fixed about each individual over time, well, that should be in there too. And we can put that in the error term. It's really in the error term right now that we have this thing that is fixed over time within individual. And it's in our error term because we haven't controlled for it. Now we just need to figure out a way to control for identity, right? And that's what we're doing when we get rid of those differences between individuals. We are controlling for identity. Now, one way that we can do it is we can literally take those axes and slide them together by subtracting out the means. We can calculate the mean of the x and y variables within each individual and subtract out those means, which slides the axes together and gets rid of all the between variation. This is called the demeaning form of fixed effects. So for each variable x and y and whatever other controls there are in the data, we get the mean of those variables within the individual and we subtract them out and we work with the demeaned data, right? So we take x, we subtract out the mean of x, and then we work with this variable instead of the original version. So we would regress the demeaned y on the demeaned x. And the result that we get will have controlled for the individual fixed effects. So it will have removed all the between variation. You can do this by hand fairly easily using group by and mutate. So for example, here we take our crime data set, we group by county, so it's going to do the calculations by county. I can get the mean within counties by just doing mutate to get the mean of the crime rate and the mean of the probability of arrest. Because I did group by county first, it's going to calculate that mean for each county separately. Then I can get the demeaned version by simply taking the original crime rate and subtracting out the mean of the crime rate within county, and what remains is the demeaned version, which will give me the fixed effects result with all of the between variation controlled for. The other main way that we can do this is with what's called the least squares dummy variable approach. And what this is that we are just going to add a binary variable for each individual. Except for one, of course, we need to have that reference group. So we are literally adding individual as a control, which is another good way of thinking about the fact that this is really controlling for individual. So we can do that. All we have to do is take whatever our regression was. Here's the crime rate regressed on the probability of arrest, and then we add on a set of binary variables for our individual, which in this case is county. If we wrap it with that in factor, it will automatically treat it as a set of binary variables and include each of those individually. And you can see, by the way, that this result that I get from using the demeaned result gives me the exact same result as doing it with the least squares dummy variable approach. The only main difference is that our squareds are different, but that's because they're measuring two different things. This is giving you the r squared of the just the within variation. How much of the within variation in x explains the within variation in y. And this r squared includes the part that is explained by the fixed effects themselves because they're actually included in the regression. So neither of them is better than the other. Neither of them is wrong. They're just answering different questions. So how can we interpret these results once we have them? Well, we have a negative 0.03 here, and remember the dependent variable here is the crime rate, and the independent variable is the probability of arrest. And so in a typical regression, so here's just the original regression without any fixed effects in it at all. So that would be us saying that if the probability of arrest increases by 1 unit, we would expect that on average the crime rate would increase by 0.05 units. That would be the standard interpretation of an ordinary least squares result. Here we have a negative 0.03 with our fixed effects result. And remember, we can interpret this in the exact same way, it's just everything is within now. So what that's saying is, if a given county saw a 1 unit increase in their probability of arrest, we would expect that that county would see a reduction in their crime rate by 0.03, right? So it's the same idea, it's just we're comparing everything within counties or within individual over time. I will point out that if you're actually doing fixed effects in real research, you're probably not doing either of those methods. You're probably using a function that is specifically designed to do this for you. So we, in this class, are going to use the estimator package with no final E there, and the LM robust function in there, which allows fixed effects as an argument. There are a number of other packages that you could use instead. They're a bit more powerful, but maybe a little bit harder to use. There's FELM in the LFE package. There's fixest in the fixest package. But for our purposes, LM robust will work fine. It'll also, by default, use robust standard errors. Something else to note, we're not going to go super into this in class, but it is common in fixed effects analyses to cluster your standard errors, which means that you are allowing for the error terms to be correlated within individual, in this case. And that makes a lot of sense. You might expect that different individuals behave differently, or at least their error terms might be related to each other or correlated across time. And so you would allow that to occur by clustering the standard errors, and LM robust will also allow you to do that. You just set clusters equal to county as well. So that's how we can do fixed effects, and it can solve a really important problem for us. We would often think in a lot of social science situations that a lot of the endogeneity problems that we see are because of between variation. Right? Why is it difficult, for example, to tell what the effect of education on your earnings is? Well, because different kinds of people make different educational choices. And if it's something about being a certain kind of person, right, you're the kind of person who loves school. You're the kind of person who works really hard, right? Whatever it is, if that is a thing that's about you specifically, which it often is in social sciences, we can control for that by using fixed effects. If we can observe you multiple times with different kinds of schooling levels and then see what happens, we're good to go. Of course, downsides to this. So for one thing, you can't use it to study anything where that it itself is within variation, right? I can't use it to study what's the effect of having this kind of personality, if that's constant over time, because I can't, if I use fixed effects, it will control for the treatment. And you can't do that. So it can really only be used to study things that change over time for individuals. Also, it feels like you're controlling for everything you need to control for, but you're only controlling for the between variation. If there's something in the within variation that's giving you an endogeneity problem, fixed effects has nothing to do with it. It won't help. So let's say, for example, you want to know the effect of having a certain kind of government on your growth rate. Right? Well, first of all, that would be a problem because that doesn't change very often, so there's not a lot of within variation. Another problem that you might have is that, well, one reason why you might see it change over time is like if there's a war or something. But then the war, which is not a part of between variation, because within a country, sometimes it's at war and sometimes it's not. So if the reason your regime changes because of war, well, then you still have an endogeneity problem that fixed effects won't solve. Going further, it's not just that the treatment needs to vary over time, it needs to have a significant amount of variation over time. If it's something that changes very, very slowly, like I mentioned, kind of government, you're just not going to have that much variation in the treatment to be able to look at, right? All of the variation really is between countries on that, and within countries, you see a couple of changes, but there's not a lot to go on, there's not a lot to study. All right, I've gone on too long, but those are the basics of fixed effects. We are using fixed effects to try to solve an endogeneity problem where we have between and within variation, and we have a lot of endogeneity problems with our between variation, but we can control for it by getting panel data where we observe the same individuals over time, and then just comparing within individual by getting rid of all the between variation, which we can do by demeaning the data by individual, or by including a set of dummies for individuals in our regression, the least squares dummy variable approach, or of course we could just use a function specially designed for fixed effects. This will control for all of our between variation, which is great as long as we don't. I mean, as long as we don't have any endogeneity problems on the within variation, which in that case we'd still need to actively control for those things and include them in our regression, and making sure that the treatment that we're trying to understand has within variation and has a lot of within variation for us to study. Okay, I've gone on too long. Thank you very much.